Hi, this is Jiayu from Miami University, and I'll be giving the presentation for the project Price of Houses in Oxford, Cincinnati area. So the relevancy of this research applies to individuals searching for a house in the general area. With the results from the project, home buyers can be equipped with financial knowledge when deciding to move into Oxford or Cincinnati. This information would also be very useful for potential college students using housing prices to decide between attending Miami or the University of Cincinnati, or possibly deciding between job offers located in both areas. The location was a qualitative variable with two levels, having code 0 if in Oxford and code 1 if in Cincinnati. First, my team wanted to run a simple linear model. However, by looking at the pairwise plot, did not provide a clear answer of whether we should include interaction terms or revise our simple linear model, because the trend lines on the graph appear somewhat flat. So we first started with a model including all the interaction terms. To come to a final decision about our model, we used backward eliminations to further examine other models. We gradually remove any interaction term with p-value greater than 0.05. After that, we ran backward regression once again, with interaction being only sets of 2 rather than 5, and found a model that has a lower AIC than the simple linear model, which is our model 3 here. So we found a significant linear relationship between price of house and location, square footage, lot size, and number of bedrooms, bathrooms, and floors due to the p-value from the F-test being very close to 0. Also, checking the multicollinearity issue is important. We actually removed variables with VIFs greater than 10. Also, based on the Pearson correlation matrix, the result indicated that the pairwise correlation between size and numbers of bathrooms is slightly greater than 0.7. However, since the p-values for each individual predictors and interaction terms were significant, and the VIFs were all less than 10, we did not remove those two variables because we wanted our model to be more informative. Also, the diagnostic plots were checked. It showed that the normality assumption was violated. So we tried a transformation and found the best value for lambda, which was 0.5. However, the normality assumption was still violated for fitting the transformed model, and the R-square adjusted value actually decreased by forming the transformation. Since the R-square adjusted value for the untransformed model was already high, which was about 0.77, and the predictor variables were all significant, we decided to keep the untransformed model. So our final model we select has an R-square adjusted value equal to 0.77. Overall, the equation for the selected model will be price equal to a combination of location, the house size, number of bathrooms, lot size, and the interaction term between location and lot size. And here's the Pearson correlation matrix and the VIFs for the predictors for this final fitted model. So our conclusion is, if in Oxford, the best way to minimize price would be to increase the size and amount of bathrooms while limiting the amount of bedrooms, floors, and lot size. However, in Cincinnati, the best way to minimize price would be to increase the size, number of bathrooms, and the lot size, while decreasing the number of bedrooms and floors. So overall, focus on the interaction between size and location will yield cheaper housing price in Cincinnati.